There. It's already unmuted. Oh my goodness. Sorry. There. It's already unmuted.
Okay, it's unmuted, right? They can hear.
Yes.
All right, if they can hear me, that's good. So this is a low resolution image of the same nanomagnets. So we have millions of them actually on a nanomagnet. And the underlying substrate is piezoelectric. And that's important. So if you're looking at a low resolution or low magnification figure, you see this substrate is piezoelectric. And these little squares, each one of them has many nanomagnets. So this is a low resolution image of any one of these squares. And then we have two contact pads. These are made of gold or aluminum. And these are used to launch a surface acoustic wave in this piezoelectric crystal. So what the surface acoustic wave would do is it will subject these nanomagnets to periodic strain with the same frequency as the frequency of the surface acoustic wave. So this is what we call an artificial multiferroic magneto-elastic crystal. You can see why we call it crystal, because it's two-dimensional periodic. That's the reason we're calling it a crystal. Yes.
Can you share the composition of the ferromagnets?
These are cobalt ferromagnets.
Pure cobalt.
Pure cobalt.
Thank you.
Pure cobalt ferromagnets. And the piezoelectric substrate can be either PMNPT or PZT or lithium niobate. Typically, we use lithium niobate for the simple reason that it's a very low loss material for surface acoustic waves, and also it is the cheapest of all these other substrates. So the substrate's size, if you are interested in that, is about 1 centimeter by 1 centimeter in these cases. All right, so multiferroic, because you have cobalt is a magnetostrictive material, and it's important. You cannot use a non-magnetostrictive ferromagnet. You have to use a magnetostrictive ferromagnet because you need magneto-elastic coupling. And magnetostrictive ferromagnets are such that they're subjected to the Villary effect, which is the inverse magnetostrictive effect, so that if you apply strain on them, you will actually rotate the magnetization. And if you apply periodic strain, the magnetization will go back and forth. In other words, the magnetization will precess. So you'll have precessional motion in magnetization. So multiferric, this is a two-phase multiferric. It has a magnetostrictive phase and a piezoelectric phase. That's why we call it multiferric. It's not a multiferric material as such. It's just a two-phase multiferric. And it works much better than a multiferric material. All right. So now I'm frozen. Not moving. Let me just go ahead and hit the return. Nothing.
Thank you, Son.
So what's the thickness for those?
Okay, the thickness for these nanomagnets are between 2 and 15 nanometers.
No, sure.
Typically, we use 6 nanometers.
6 nanometers.
Yes.
What do you
How
do?
did you make them?
With electron beam lithography.
Huh?
So we pattern the substrate with electron beam lithography, and then we evaporate cobalt.
No, but it's
with
working now.
evaporation.
But
followed by
you,
litho.
okay.
If it stops working, how do you?
Okay, let's see. Goes back, works. Okay. So the first thing that topic that I'm going to discuss is this topic, hybrid magnetodynamical modes in this two-dimensional periodic structures. So for this, I'm going to talk about hybrid magnetodynamical modes in a single nanomagnet first. So we have, this is a high resolution or a high magnification picture of nanomagnets. So you can see these nanomagnets. These have dimensions of 190 nanometers along the major axis and 186 nanometers along the minor axis. So it's only slightly elliptical, mostly circular, if you will. And the separation, edge-to-edge separation, is 892 nanometers. So this is an ACM picture of these nanomagnets. And if you look at the MFM, the magnetic force micrograph picture, you can see that we have mixed phases. So these are not necessarily single domain nanomagnets. You have all these mixed phases that you can see. And we probe these nanomagnets with time-resolved magneto-optical Kerr effect microscopy. So there you have a pump beam and a probe beam with a delay between the two beams. And the delay can be adjusted, it can vary. So, and you have a magnetic field that is slightly tilted. And the magnetic field is necessary to set up spin precession in this. This is Kittel modes. You get the typical Kittel type spin precession in this case. And so the pump beam and probe beam, they're both ultra short laser pulses, 100 femtosecond laser pulses actually. And so the pump beam would, in the presence of the magnetic field, will set up the spin precession. And then the probe beam will actually look at two things: the reflectivity of the nanomagnets and the polarization of the reflected light. So the polarization of the reflected light is the Kerr signal, Kerr effect signal. So that will give you information about the spin wave modes inside these nanomagnets. So in this case, we're looking at cobalt nanomagnets on a PMN-PT substrate. And the pitch of the array, which is the center to center separation, is 1.078 microns in this case. Okay. So that's important. Why is it important? Because now we can actually focus a laser spot, which has a size of 1 micron, on a single nanomagnet and probe a single nanomagnet without any effect from the other nanomagnets. Okay, so the magnetic field, as I said, is there to induce spin precession. Now, even though we don't launch any external surface acoustic wave in these nanomagnets, there is still one. And why does that come from? Well, there is periodic heating and cooling by the pump probe beam, and it causes periodic strain in the substrate because of the unequal expansion and contraction of the nanomagnets and substrate. There's some periodic strain being generated. We actually see that periodic strain. And so that effectively produces a surface acoustic wave, even though we don't launch a surface acoustic wave from outside in the sample. So there's always this surface acoustic wave because of the periodic heating and cooling by the pump and probe beam. Okay, oops. And what does this surface acoustic wave do? It modulates the precessional dynamics of spin in a single nanomagnet to spawn hybrid magnetodynamical modes. So these modes have a mixed character. They are a result of magnon-phonon coupling, the phonons coming from the surface acoustic wave generated by the periodic heating and cooling. And the magnons are the quanta of the spin waves that are formed in the nanomagnets because of this magnetic field here that we call Kittel type spin precession. So we have hybridization of magnons and phonons, and the resulting modes we call hybrid magnetodynamical modes. So let's see what we get. The first thing is that we know that there is a SAW because of the periodic heating and cooling. So to prove that, we actually look at the reflectivity of the substrate in our TR-MOKE setup. And you can see some oscillations. And if you go and do a fast Fourier transform of these oscillations, you see 3 distinct peaks at 2 gigahertz frequency, 8 and 16 gigahertz. Now, where do they come from? So let's look at the first one, 2 gigahertz. The SAW wavelength at 2 gigahertz is obtained from this relation. The velocity of the SAW is the product of the wavelength and frequency. Frequency is 2 gigahertz. Velocity of SAW in 001 PMN-PT substrate is 2 kilometers per second. So you can see that the wavelength corresponding to this mode here, the 2 gigahertz mode, is 1 micron. And remember what this 1 micron is. is the pitch of the array. Okay, so it's the pitch of the array is 1 micron. So it's the distance center to center between the two nanomagnets. So we have a resonance effect here. The SAW is periodically reflected. You have distributed reflectors. The magnets are acting as reflectors of the SAW, and that is setting up a resonant mode at 2 gigahertz, and that's what you see in the Kerr oscillations. That's the 2 gigahertz. And the 8 and 16 are higher harmonics of this. So the SAW wavelength corresponds to the pitch of the array. We are not the first to see this effect, yes.
I just want some details about the compound deploy. What was the red wave
So the pump beam and the probe beam wavelength is 800 nanometers. The repetition rate, I don't remember that, but the delay between the pump and the probe beam is varied, and that is this one. This time axis is actually the delay between the pump and the probe. So damping effects would show up if there is any in this. The pump induces the spin precession, and then the probe probes it as a function of time. And as you go to higher delays, the spin waves will decay, attenuate, and you see that damping. But here, of course, there's hardly any damping.
But you're assuming.
But the repetition rate, I don't remember exactly what that.
You're assuming that between pairs of constants, the system has thermalized.
The system is always thermalized. There is just a periodic heating and cooling because of the but the time for that heating to relax is actually shorter than the time between that. So that's why you see that effect. Otherwise, of course, you wouldn't see it. Oh, go back. So, like I said, I mean, this 2 gigahertz mode corresponds to the wavelength that is equal to the separation, the periodicity of the array. So then the next thing we do is look at the Kerr oscillations. So Kerr oscillations are different from reflective. Kerr oscillations are looking at the polarization of the reflected light. So this is the experiment. This is the Kerr oscillation as a function of the delay between pump and probe. And then if you do the frequency, the fast Fourier transform of this, you will see the spectrum in this oscillation. And you can see that there are 3 different peaks: low frequency FL, medium frequency F, and high frequency FH. So 3 peaks show up, and then we can actually simulate the spin wave dynamics. So how do you do the simulation? Well, we actually use either MuMax3 or OOM, which are micromagnetic simulation packages. And the strain in a magnetostrictive material acts like an effective magnetic field. So it has the same frequency as the frequency of the strain, periodic strain. And the amplitude of that effective magnetic field can be related to the strain power, the power in the strain, and we'll talk about that a little later. There's a way to do that, and I will show you that a little later. And so that's how we do the simulation. And you can see that the simulation and the experiments have reasonably good matching. There are some extra peaks that you can see in this simulation, which we don't really see in the experiment. And these peaks are somewhat subdued, and maybe we don't have enough experimental resolution to see them, or maybe these peaks are spurious. You can see spurious peaks, and that I will talk about later why you can. We don't know for sure whether these are spurious peaks and that is why we are not seeing them, or because they are not spurious, they're actually there, but we don't see them because we don't have enough sensitivity. So either one of them is possible. Now, how do you do the simulations? So the way to do the simulations is they're based on this package called MuMax3, which is a standard package for simulating magnetodynamics. The SAW-induced periodic strain anisotropy is a model like this, that there are 2 terms here. Why 2 terms? Because we can see that, go back, we see that there are 3 frequencies. 16 gigahertz is too higher frequency, nothing will respond to that. So forget about the 16, we keep the 2 and the 8. So those are the 2 frequencies that will go in here, F1 and F2. 2 dominant SAW frequencies that we see in our previous experiment. And this K0, this quantity is treated as a fitting parameter. So you get the best fit at K0 is this, and the magnetostriction coefficient of cobalt is this. So from this K0 value and the magnetostriction, you can actually estimate the value of the stress that is being produced in a single nanomagnet by the laser heating and cooling. And that turns out to be 375 megapascals, which is a very reasonable number. And this corresponds to this, the Young's modulus of cobalt. So from there, you can get the strain from the stress, and the strain is 0.18%. That is how much strain you're producing in the single nanomagnets. Now, we can then, once we have all of this, we can extract the magnetization coefficients in the x, y, and z directions, 3 dimensions, as a function of the coordinates x, y, z, and time t. And then you can Fourier transform this to get this results, the simulation results. So that's how the simulations are done. All right. So now we take these modes. You can see that we have 3, keep this in mind, that we have 3 dominant modes, FL, F, and FH in the spectra. And so we then plot these 3 modes as a function of biased magnetic field. We measured this at different magnetic fields. So you can see that we measured it at 650 oersteds, 700, 800, 900, 1000 oersteds. And then we actually plot this as a function of the frequencies of these modes as a function of magnetic field. So the 3 modes, FL, F, and FH, that all 3 of them are plotted as a function of magnetic field. And then this dotted line is the simulation result. So you can see that for the lower, the 2 modes here, that is FL and FH, we match pretty well. But for the other one, we don't match as well, the higher mode, FH. There are some discrepancies. These are the error bars. And then we can also look at how this behaves as a function of the pump power, pump beam power of fluids. So this is the pump fluids, millijoule per centimeter square. And you can see that they actually go down a little bit with the pump fluids. Now, none of these modes can be fitted with the Kittel formula for magnetic field dependence. So none of this do not obey the Kittel formula. So clearly they are not Kittel modes. They're not spin wave, pure spin wave modes. They're hybrid magnetodynamical modes, born of mixing between the SAW modes and the Kittel spin wave modes. And note that they're probed in a single nanomagnet. So you're looking at it in a single nanomagnet, not in the whole array. The whole array will have other complicated effects due to dipole coupling between neighboring nanomagnets. Okay, so the other thing that we can do is we can actually simulate the power and phase profile of the spin waves that are created in the nanomagnets. And so we do that for the 3 different modes, FL, F, and FH. And you can see that we do this at different magnetic fields, 650, 700, etc. And we calculate the power and phase profile. And you can see that in most cases, these modes are edge modes, meaning that the power is concentrated at the edge. So there's unfortunately not I forgot to put the color bar here. Red is high power and blue is low power. So the power is concentrated at the edges. In this case, for FL, the first mode, the low frequency mode. For F mode, it's the other way around. Power is concentrated at the middle. So their power and phase profiles change a lot. This is the power profile and this is the phase profile. They change a lot depending on the magnetic field and are very different from the 3 different modes, F and FH. So there's a lot of rich physics in this, that we have this very peculiar spin wave power and phase profiles under in the hybrid magnetodynamical modes. So, oops, go back, it's going too fast. So how do we calculate this? Well, again, from the MuMax micromagnetic program, we get the magnetization. Then what we do is we Fourier transform with respect to time, and at one location Z is, so we do this on the surface of the nanomagnets. So we put Z equal to the surface. And then once we have that, we do the Fourier transform, first Fourier transform. And then we get, that will give us this. And then the power is 20 log 10 that, and the phase is this. So that's how we calculate this power and phase profiles. It's in this paper. So, yeah.
Do you know why you have this coexistence of different modes?
So the thing is that you have coupling between this, the spin wave. You can have multiple spin wave modes excited in a nanomagnet at a given magnetic field, even without any phonons, even without any circuits. And the reason being that this spin wave modes can go and look at the magnet. The shape of the magnet is slightly elliptical, right? So you can have modes, one mode along this direction, different mode along that direction, etc. So you can have more than one mode because of the odd shape of the magnet. So that is why you can have coexistence of multiple modes inside a magnet. And then, of course, when you bring in the phonons from the saw, that becomes even more complicated because you have this hybridization going on. And that's the reason of, because of that hybridization, we have this crazy power and phase profiles that we see. Yes.
This software that you mentioned, does it assume like some particular spin wave excitation mechanism?
No. So mu-max is basically solving Landau-Lifshitz-Gilbert equation.
Like, how are you coupling that pump to your?
So the pump, so we have the saw, the periodic strain, that is what matters. Because that is what the pump and the pump boom generates. So the periodic strain acts like a periodic magnetic field. And what you do is you equate the power in that magnetic field to the power in the strain field. And by equating the two, you can come up with the amplitude for the magnetic field. And that amplitude goes into the mu-max or micromagnetic simulator to replicate the effect of the strain. So that's how we do the theory.
It's like indirectly changing the exchange coupling.
No, not exchange coupling. It's a Landau-Lifshitz-Gilbert equation as a magnetic field turbine.
It has an astropactic.
So yeah, so you add another additional magnetic field to that because of the strain.
So by looking at your frequency spectrum, looks like you have equal spacing. Then
No, not yet. No, this is not equal spacing.
Okay, so I'm okay.
Not equal spacing. If you look at it, it's not really equal spacing. It may look like equal spacing too, but it's not.
So there's no full magnet scattering here.
No.
Okay.
None of that.
Okay.
We'll talk about equal spacing later. So the next topic that I want to talk about is amplification of intrinsic magnon modes. So you can see that because of the periodic pump and probe and the magnetic precession caused by the magnetic field that we have present here, the Kittel mode. Because of that, you will have these modes, and these are intrinsic to the array. What do I mean by intrinsic to the array? They depend on the magnet shell size, shape, spacing, etc., periodicity, pitch, etc. So we call them intrinsic modes because they are intrinsic to the array, right? Now, the next thing that we want to do is now we will have, in addition to the saw generated by the pump and probe, we will launch a saw from an external source. So now there's an additional saw, and that saw power is much higher. Okay, so now we will look at what happens when you launch an external saw into this array. Now you can launch this saw at a frequency that corresponds to one of the intrinsic mode frequencies, at FL or FH or F. Or you can launch the saw at a completely different frequency, right? So what happens is, if you launch a saw at one of the intrinsic frequencies, that mode is amplified because the saw power gets transferred to that mode, and that mode goes up in amplitude. And if you launch a saw at a completely different frequency that does not correspond to any of the intrinsic modes, Then you will get an additional mode that will be at the launched SAW frequency. We call that an extrinsic mode because it is not present normally. It is present only when you launch an external SAW. Okay, so that's the picture here. Again, you have the same picture, except now you have electrodes to launch external SAW into this array. Okay. And I just want to point out that our laser spot size is about 1 micron. So in this array, it covers about 4 nanomagnets. So we are always probing 4 nanomagnets at a time. So your signal is coming from just 4 nanomagnets. So what happens in this case? So first, you do not launch any SAW, no SAW, and you look at the intrinsic oscillation. So this is reflectivity measured by the same Kerr microscope, and this is the Kerr oscillation. So this is the intensity of the reflected light. This is the polarization of the reflected light. All right, so then you do the Fourier transform of this, and you'll see these peaks. And now you see 4 peaks at there. 1, 2, 3, and 4. These are intrinsic modes. No external SAW is present here. These are all intrinsic modes. Because the array is different, now you have 4 intrinsic modes instead of 3. So how many modes you have and what their natures are depend on, will vary from one arrangement to another arrangement. It depends on the nanomagnet size, shape, and spacing. So again, you can look at the power and phase profiles of these 4. These are because our spot size is just large enough to cover 4 nanomagnets. So we have 4 nanomagnets here. And you have 4 modes, 1, 2, 3, 4. And we have, these are the 4 modes, M1, M2, M3, and M4. So we calculate the power and phase profiles of these modes. No SAW, right? There's no external SAW present. Then we apply the external SAW. No SAW present. Intrinsic modes showing up. 4 intrinsic modes, and they occur at these frequencies, 3.1 gigahertz, 4.2 gigahertz, 7.1, and 10.2. And power in the lower frequency modes is much higher than those in the 2 higher frequency modes. This has to do with the internal dynamics of the array. So this will change if you have a different array. All right, now we apply SAW. And the SAW wave is propagating along the major axis of the elliptical nanomagnets. So now see what happens. Right. So what happens is when the SAW is not resonant with an intrinsic frequency. So remember the intrinsic frequencies, keep this in mind. The intrinsic frequencies are 3, 4, 7, and 10 gigahertz, right? So if you launch a SAW at say 1 gigahertz, which is not one of the intrinsic frequencies, what will happen is the intrinsic frequencies are not affected very much. You still see these peaks, but now you see an additional peak at 1 gigahertz. This is 1 gigahertz. So the star peak, this is the new peak that came up when you launched the SAW, and this is obviously because of the SAW, it occurs at the frequency of the SAW. So again, this is the experimental result in the simulation results. And then you go to 3 gigahertz. 3 gigahertz is an intrinsic frequency, one of the intrinsic frequencies. So what happens is that the mode that was at 3 gigahertz gets amplified, much higher amplitude. So you can go on and do this. This effect is less pronounced at the higher frequencies, but this is more pronounced at the lower frequencies. So when the SAW frequency is not resonant with an intrinsic frequency, it generates an extrinsic mode at its own frequency like this one, 1 gigahertz. 1 gigahertz is not an intrinsic frequency, so the SAW just created a peak at that frequency. When the SAW frequency is resonant with an intrinsic frequency, then what happens, it amplifies the mode at that frequency while attenuating all other intrinsic mode. So this is very strong phonon-magnon coupling. Power from the phonons in the SAW is getting coupled into the corresponding magnon mode at the same frequency and amplifying that magnon mode. That is why the peak goes on. And power is transferred from the SAW to the resonant mode, showing phonon-magnon coupling. Examples are at 3 gigahertz and 4 gigahertz. You can see that the peak is amplified a lot at 4 gigahertz, strong peak, both in simulation and theory. There are intrinsic modes at this frequency, and SAWs of this frequency are launched. The intrinsic mode powers are amplified by 7.2 times for the 3 gigahertz and 4 times for the 4 gigahertz. The effect is less pronounced in high frequencies. So now, yeah,
So making these things, but how do you launch the SAW in these things?
so the SAW is launched by these electrodes. So we have this is a piezoelectric substrate. So you apply a AC voltage between these 2 electrodes, and that causes a periodic strain in this piezoelectric substrate, and then launches it. This is not the Rayleigh mode, but this is all. It's a mixture of all modes. The Rayleigh, Cesar, and Lamb modes of SAW. All right. So now we are looking at the previous case. The SAW was propagating along the major axis of the nanomagnets. Now let's see if there's a directional effect. What happens if the SAW is propagating along the minor axis of the elliptical nanomagnets? So that's the case here. And you can see that it is very different. There is a strong directional dependence. So this is the simulation, this is the experiment. Let's look at the experiment. So if you launch a SAW propagating along the minor axis at 4 gigahertz, what do we see? We see that this is the 4 gigahertz peak, it gets amplified. Launch a SAW at 7 gigahertz, which is also an intrinsic mode frequency. That one gets amplified, but the 4 gigahertz stays there, doesn't go away. Launch a SAW at 10 gigahertz, another intrinsic mode frequency. That mode is amplified. 4 gigahertz stays there, doesn't go away. So the 4 gigahertz doesn't go away. This is not a feature that we observed in the other case when the SAW was propagating along the major axis. But we observed this feature along the minor axis when we launched the SAW on the minor axis. So what is this due to? Okay, so at any driving SAW frequency, the resonant intrinsic mode is amplified, but the non-resonant frequency mode, see, they're all other 3, 7, etc. They're all gone. They're drastically suppressed, a feature that is not observed in the case of SAW propagation along the major axis. And the exception is the strange 4 gigahertz mode. It never goes away. Even when the SAW frequency is non-resonant in this mode, it survives and it's not suppressed. And so what is this? And it believed that this mode has nothing to do with the external SAW, but it is the internal SAW that is generated due to laser heating and cooling. So nothing happens. Yeah.
So the 4 gigahertz mode that is like being observed, is that along the major axis still, or that is along the minor axis?
So this is when the SAW is propagating along the minor axis. This mode is all over the place inside the nanomagnet, but the SAW is propagating along the minor axis of the nanomagnets. All right, so the nature of, so this is very interesting that the nature of magnon-phonon coupling in these systems is anisotropic. Yeah.
So for the 4 gigahertz mode, the line width is actually because it becomes smaller.
That is probably true, but we don't, so that means that this mode becomes less lossy.
Yeah.
Right? It becomes less lossy. And we haven't studied that. That's an interesting observation that line width is becoming smaller and smaller. Why is it becoming less lossy? I don't know. I mean, why is it becoming less lossy?
So look like with SAW, some kind of damping mechanism was killed.
Some kind of damping mechanism was probably killed. That is, but we don't know what that mechanism is. All right. Then the next topic, third topic, I want to talk about tripartite magnon-phonon magnons. So previously, all I had talked about was magnon-phonon coupling, which is a 2-body coupling, magnon and a phonon. Now I'm going to talk about 3-body. So there is a magnon, there's a phonon, and there's another magnon, the second magnon coupling, and the formation of a new quasi-particle that we call the binary magnon-polaron. So what is this thing here? So in this case, we have similar setup. And we look at the Kerr oscillations again. So this is the reflectivity and this is the Kerr rotation. In the Kerr rotation, we see that there are 2 dominant peaks. So there are 2 dominant magnons, 2 dominant spin waves in these systems. Okay. So no external SAW is launched, but there's a bias magnetic field. That's always there. The bias magnetic field not shown here, but it is there to induce Kittel type spin waves. And that field in this case is 900 oysters along the major axis of the ellipse. That's the bias magnetic field. Two spin wave modes that we see at 4.5 and 9.6, but they're not of the same nature. This one, the 4.5, is actually due to laser heating and cooling. This one is a Kittel type spin wave mode, and we'll talk about that. So the 4.5 gigahertz mode shows up in both reflectivity spectrum and in the Kerr oscillation spectrum. So this is certainly due to the SAW that is generated by periodic heating and cooling. This one, however, is not that. So let's see what this one, the higher frequency 9.6 gigahertz mode is. So we have to plot both modes as a function of magnetic field. So we do. These are experimental results. The dotted lines are all experimental results, and this white curve is theoretical fit to this. And this white curve obeys exactly the Kittel relation. It's telling us this mode, the one that I showed at 9 gigahertz at 900 oyster, that one is a normal garden variety Kittel type mode. This one is the SAW causing a spin wave mode, and the frequency of the SAW in this case is due to periodic laser heating and cooling. And we can show the power and phase profiles. Two different magnetic fields, 400 oysters and 1200 oysters. Here at least I have the color bar, so you can see that these are all center modes. Power is concentrated in the center of the nanomagnets. Okay. The 4.5 gigahertz mode, which is this red one, E1, we call it E1 mode, it does not change with magnetic field as expected, because it's due to periodic laser heating and cooling, and hence should not have a dependence on magnetic field. The other one changes with magnetic field, increases magnetic field, and actually satisfies the Kittel relation. It is therefore a Kittel mode. And this is the power and phase profiles at two different magnetic fields. Note that the M1 mode, which is this one, the one that I'm being showing here, is a center mode, meaning the power is concentrated at the center. All right. I don't know what I missed. The points are, so like I said, this, the points here are experimental, and the white line is a gray line is simulated. Okay, now we turn on a SAW, which was not previously present. Turn on a SAW at 12 gigahertz. And now everything changes. The dispersion relations change completely. So now, first of all, we have 6 modes instead of 2. Previously, we had a 4.5 and 9.6 gigahertz, now many modes, 6 modes. The 2 modes that obey the Kittel relation, which are spin wave modes, are M1 and M1 prime and M1 double prime. So you can see the yellow and the green, these two. The yellow mode, which comes down and bends upward, and the green mode, right? So we can actually take a zoomed view inside this yellow rectangle. So this is a zoomed view. And what you see is that there is anti-crossing. Right? So the yellow mode comes down, goes up, and the green mode does this. So they veer away from each other. This anti-crossing is a telltale sign of coupling. These 2 modes, M1 prime and M2 prime, M1 prime and M1 double prime, they're coupling at that particular magnetic field, 1200 oysters. Strong coupling between them. That is why you have this anti-crossing. So you can actually look at the power and phase profiles at 3 different magnetic fields, including the where magnetic field of 1200 oysters, that this anti-coupling occurs, right? So now look at what happens to this mode here, E1 mode, all right? So we'll look at this. The A1 mode at 12 gigahertz is obviously due to the SAW, and this is in this mode here, the blue. You can see this blue mode, that's A1. So A1, it is at 12 gigahertz, and we lost a 12 gigahertz SAW. So that is due to the external SAW that was launched. And it is magnetic field independent because the external saw mode has nothing to do with any magnetic field. The power spectra at 1200 oersteds. So let me show you this. So this is the power spectra at 1200 oersteds, where this anti-crossing occurs and maximum coupling takes place. And you can see that the A1 mode has completely disappeared. It's not there. You can see these other modes. Now the A1 mode should have been somewhere here. At A1 mode is at 12 gigahertz. It should run somewhere here. It's not there. It's gone completely. It's gone. What happened to it? Well, what happened to it is all the power from this A1 mode got coupled into these two modes, causing the strong coupling between these two magnets. So this is almost 100% coupling, because 100% of the power from the coupling agent, which is the A1 mode, went into this. So this is three-body coupling, tripartite coupling. Two magnon modes, M1 prime and M1 double prime, two magnons, were coupled by this A1 mode, which is a phonon mode. This is a SAW mode, surface acoustical wave mode. So the phonon coupled two magnons and coupled it so that the phonon power got completely transferred into these two magnon modes. Right? So the A1 mode has coupled A1 and A1 prime modes at 1200 oersted frequency, transferring 100% of its power to these two spin wave. The A1 mode is due to launch SAW and has the frequency of that SAW. The phonons from that SAW have coupled the magnons in M1 and M1 prime. We call this tripartite magnon-phonon-magnon coupling. Now let's look at the cooperativity factor. The people here are familiar with, yeah.
Sorry, I got a little bit confused with this notation. Like, how do we know that A mode is like phononic in nature?
Because the A1 mode, you can see the A1 mode here is this blue line. It occurs at 12 gigahertz and it does not depend on magnetic. And we have a SAW present at 12 gigahertz. So this mode has to come from that SAW. There's no other possibility. So SAW means that's phonon. SAW is phonons. This E1 mode, the low frequency mode. So this is due to the periodic heating and cooling of the laser, the 4.5.
So how should I think of it? Like,
So you have two different sources of SAW here. You have an external SAW that is launched, that is at this mode, blue mode here. That's the 12 gigahertz. And then there's an internal SAW due to periodic laser heating and cooling that is at 4.5 gigahertz. That one we don't care about.
but this is also phononic in nature.
Both are phononic. Yeah, both are phononic. This one doesn't do anything, this one does. Right? So, how many of you know about cooperativity factor in coupling? Oh, you know, Benjamin of course does. Cooperativity factor in coupling. So cooperativity factor is a measure of the strength of coupling. So how do you calculate the cooperativity factor? So you take the splitting, right? Here, the two are going away from each other. The two more. And so they anti-cross here. So you look at the anti-cross and you see the splitting. Okay, so that is an indicative of the strength of coupling. The larger the splitting, more the coupling strength. And then the other thing that you need to know is what is the loss rate. So loss rate of this, you can look at the peak widths, and from the peak widths, full width at half maximum, you can calculate the loss rate. And these two quantities determine the cooperativity factor. And if the cooperativity factor is greater than 1, then we say it's strong coupling. If it's less than 1, it's weak coupling, right? So these are the cooperativity factors. And you can see that they're always greater than 1. So we actually have strong coupling taking place between the two magnets. Yes, did you have a question? Okay, all right. So large cooperativity factor. And the cooperativity factor exceeding unit is indicative of strong coupling and suggests the formation of new quasi-particles. So in this case, the two magnons and the phonons are coupled so strongly with each other that all three of them have lost their individual character. Now you cannot view them as a magnon and a phonon because they're so strongly coupled together, and they have lost their individual character, and we call such a quasi-particle binary magnon-polaron. Now, yeah.
What's the reason, like, what's the special of this configuration that gives you that strong coupling?
Okay, so why we see that strong coupling and we don't see it always has to do with the fact that in this particular case, we could match three things. We could match with the magnetic field. We could match the frequency of the magnons. That happened to coincide with the frequency of the surface acoustic wave, right? So you need to have what we call phase matching to get strong coupling. The frequency has to match. And in this case, the frequency match. We can actually engineer this because the magnon frequency is a Kittel mode, so it can be changed with the magnetic field. So we picked the magnetic field and the array parameters judiciously here, such that the frequencies match of the two magnon modes and the phonon mode. All three of the frequencies match, and that's why we can do this.
And
So there's some engineering involved here.
you're probing over 4 dots, right? For
Four
nanomagnets.
dots, yes, yes.
And
But we can move it to another set of 4, and we'll still see this effect. There will be some slight variations, but we'll still see this effect.
are the magnon modes launch with the same phase in the 4 dots?
So we can look at the phase. We'll talk about phases, but there's very interesting things happen with the phase. But you can look at the phase profiles. These are the phase profiles. See the phase profiles in the dots. But we'll talk about phase profile a little bit later. There's something very interesting.
Rephrase the question. If you were able to measure a single dot, a single nanomagnet, would you still be able to see this crossing?
Yeah,
Yes.
probably, yes. You should be able to see this crossing because this crossing depends on matching the magnetic field or engineering the magnetic field to match the phonon frequency with the two magnon frequencies. So this is a new quasi-particle, binary magnon-phonon. Okay, now some interesting features. Directional dependence. This is SAW propagating along the major axis of the nanomagnets. This is SAW propagating along. Oh, this is actually not SAW. I'm sorry. This is the magnetic field along the major axis of the magnet. This is the magnetic field along the minor axis. There's also directional dependence on the SAW. But let's look at the directional dependence of the magnetic field that we have. What is the magnetic field for? It is to induce the Kittel modes, to create the Kittel modes. So at the magnetic field where coupling occurs, you can see first of all 2 things. The difference is that this anti-crossing occurs at 1200 oersteds. Here the anti-crossing occurs at 650 oersteds. So almost at half the field. So the frequency at which they match is different. There's some directional dependence on this. So at the magnetic field where coupling occurs, now you're talking about the phase profiles. They show azimuthically quantized behavior with quantization number equal to 2. So in this case, we are covering 4 nanomagnets. And these 4 nanomagnets are more or less identical. So instead of showing 4, we show only 3, and the 4th one is not the power, but the phase. The first 3 we show the power. There's no need to show the power here because it will be the same as the others. No difference. So we showed 3 to show that there is no difference between these 3. So no need to show the 4th. That would be superfluous. So instead we show the phase in the 4th one. So you can see the phase. Okay. And thing that you note is that the phase profiles at the point of coupling, so in this case at 1200 gigahertz, or in that case at 650, not gigahertz, 1200 oersteds, and in that case 650 oersteds. The phase profiles are exactly out of phase. Hence, the 2 spin precessions associated with these 2 modes, M1 and M1 prime, are taking place in opposite directions. If one is rotating clockwise, the other is rotating counterclockwise. But we do not know. We just know that they're opposite in direction, but we do not know which is clockwise and which is anti-clockwise. So this is an entangled state. So we call the counterclockwise as C and anti-clockwise as A. The coupled mode can be written as a entangled state, right? So which is a Bell basis state reminiscent of EPR entangled states. But the system is classical. So you all know what the EPR paradox is. So in this case, the EPR paradox is I have two spins that are anti-parallel, and I take them and send one to New York and send one to Tokyo. And we make a measurement on the spin in Tokyo and find its upspin. We know immediately that the spin in New York is downspin. That's the EPR paradox. So information traveled instantaneously in time. And this is quantum non-locality that causes this to happen. In this case, we have two spin wave modes rotating in opposite directions. And so we know that one is rotating clockwise, one is rotating anti-clockwise. We don't know which one is which. So it's an entangled state because the state cannot be written as the tensor product of anti-clockwise and clockwise states. However, this is not quantum non-locality. Because if I take one spin wave mode, send it to Tokyo, the other to New York, they're no longer doing this because they have to have that coupling between them. And that coupling is caused by the phonon. And the phonon is not non-local, it's local. So it is local, there's no quantum non-locality. So this is not exactly the EPR paradox, but it's similar. So it because there's no quantum non-locality, you could not do quantum teleportation, for example. But whether you can do quantum computing, I don't know, maybe. Okay. So that's the thing. It's very interesting that this happens. Now, the next thing that I wanted to put, the third thing, and this is a new field that we started looking at, and been looking at it for slightly more than a year now. This is called acousto-plasmonic. So what we do here is we don't have a piezoelectric substrate. We have a silicon substrate. On top of that, we deposit a layer of aluminum, which is a plasmonic material. And then on top of that, we deposit cobalt nanomagnets. So this is the ACM picture. The aluminum layer is about a micron thick, which is why it's not very smooth. You can see it's not smooth. That doesn't matter. So what do we see in this case? So in this case, there are two sets of samples we have prepared, one with aluminum and the other without it. So aluminum is a source of plasmons. The one without aluminum has no plasmons. The one with aluminum has plasmons. So let's look at the one without plasmons, no aluminum. So you look at that and you look at the Kerr oscillation spectra, and you see that you have all these modes. And if you look at the simulations, you see some of them, not all of them, but 1 to 3 can be replicated in the simulations, these modes that are experimentally present and also present in the simulations. The others are experimentally observed peaks, but they cannot be replicated in the simulation. And so we don't know whether we can take them seriously. Yes.
What's the scale on the y-axis? Sorry, my eyesight is not even up.
This is the Kerr rotation.
Yeah, so it's done milli-degrees.
Milli-degrees, yeah, rotation
So you
angle.
have a precision of 0.1 microdegrees.
This is this is a milli-degrees. This is done with some, don't pay too much attention to it. It's done with some assumption that goes into it with what the.
Because microdegrees, less than microdegrees precision of the Kerr measurement is really tough.
So you can see that this is actually microdegrees. And there's enough Kerr signal here that we can say that it is microdegrees of precession that is taking place. So these are still small amplitude. Microdegrees is still small amplitude, it's not already by.
Yeah, it's not an easy measurement.
No, but we have enough sensitivity to do this. And the power, you can see that we threw away all the high frequency peaks because we could not actually replicate them in the theory. And then we looked at those 3 peaks that we could replicate in theory. And then we plotted them versus the magnetic field. And we see we have 3 modes, 1, 2, 3. 3 of these modes, 1, 2, and 3 modes, right? And this is their magnetic field dependence. 1 and 2 follow the Kittel formula, obey the Kittel formula, and is definitely a Kittel mode. 3 is not a pure Kittel mode. So it has some mixture of this is basically a hybrid magnetodynamical mode. There's some mixture of the phonons coming from the periodic heating and cooling of the laser being mixed into the spin wave. Okay. All right, then we have plasmons. So we now have a sample of them. And now see what has happened. First thing you see is we have 4 modes that are equally spaced in frequency. This is a frequency group at 1, 2, 3, and 4. And you can actually see that these 4 frequencies are magnetic field independent. So you plot these frequencies as a function of magnetic field, mode 1, mode 2, mode 3, mode 4. And you can see that there is no dependence in magnetic field. So these are not Kittel modes for sure, because they have no magnetic field dependence. They're equally spaced in frequency. So where do they come from? That is very intriguing. They are unaffected by magnetic field, and the surface plot of the power spectra are shown here, and so you can see that. The teeth span 2 octaves. Right, so they go from 1, 2, 3, and 4, so 2 octaves at micro frequencies. Optical frequency combs occur at optical frequencies. This is a completely different frequency range, micro frequencies. So where do they come from? So first of all, we looked at the reflectivity spectrum to see the periodic heating and cooling by the laser and saw that. So you can see that it does have that feature, and there are 2 frequencies here. F1 and F2, F1 much larger than F2, and this F1 is exactly at 1 gigahertz. So now go back and look at the spacing. 1 gigahertz. So this mode that we have here, going forward. This mode that we have here due to periodic laser heating and cooling is causing nonlinear coupling between magnons and phonons, and that is giving rise to this frequency group here. And the spacing is exactly 1 gigahertz that we should read. So where is this coming from? What is causing this? This field due to periodic laser heating and cooling, that's a phonon field. And then there's a plasmon field. And plasmon frequencies are very different from magnon or phonon frequencies. So normally they will not mix. However, it's a strange character of phonons. They're very friendly. They like to mix with everybody. And so these phonons actually mix, even though they're hugely different in frequencies from plasmons, they actually mix. And so these are a bunch of theoretical papers that talk about this effect, about magnon-phonon, phonon-plasmon coupling. And phonon-plasmon coupling gives rise to hybrid phonon-plasmon wave, which seems to have frequencies of gigahertz and therefore comparable with the frequency of the magnon. And so this hybridized phonon-plasmon mode is causing coupling with the magnons and causing this spin wave frequency groups. So this is the phonons. The phonons from this saw hybridize with plasmons from aluminum to spawn hybrid phonon-plasmon modes, dominantly at the phonon frequency, SAW frequency, and these hybrid modes couple with magnons to produce the frequency groups. Note that the dominant SAW mode is at 1 gigahertz. We measured it, and the frequency group teeth have the spacing of 1 gigahertz. It tells us that the hybrid phonon-plasmon mode of 1 gigahertz is causing the frequency group by a nonlinear mix. So this is an example of tripartite phonon-plasmon-magnon coupling. So you had 3 different particles. In the previous case, it was magnon-phonon-magnon coupling. 2 similar particles, magnon-magnon, and 1 phonon. Here, 3 dissimilar particles. Phonon-plasmon-magnon coupling. Okay. At higher frequencies, you actually have Kittel modes. So those were at 1, 2, 3, 4. Right? From 5 gigahertz onward, you have Kittel modes also. Now, if you actually plot the frequency Coombe modes, which are magnetic field independent, and the Kittel modes, which are magnetic field dependent, there is actually a significant difference in the power. So this is, you can see 10 to the minus 7, 10 to the minus 9, 2 orders of magnitude difference in the power. The field independent modes, which are the frequency Coombes, are 100 times more powerful than the Kittel modes in this case. And if you average over the magnetic fields, the samples without aluminum and the samples with aluminum, there is a 200 factor of 200 difference in the power. So this average peak to peak car rotation amplitude average of all modes in the plasmonic sample and in the non-plasmonic sample as a function of the bias magnetic field plotted here. There's at least an order of magnitude difference in the power. The amplitudes of the field independent modes are 200 times larger than the amplitudes of the field dependent modes. So the power is getting transferred from the hybrid phonon-plasmon mode into the spin wave modes to make the power in the frequency pools 200 times larger than the power in the spin wave modes, in the Kittel modes. Possibility of parametric amplification. So this is similar to parametric amplification, that you're taking power from one mode, transferring into a different mode. Okay, so that's my talk. And there are many interesting coupling phenomena between various types of waves in these artificial 2D magneto-elastic crystals. Now we're extending the studies to topological insulator substrates, and we see similar features. And we've already observed magnon-photon coupling and radiation of electromagnetic waves of photons. This we've already seen. The new field of coupling phenomena in the systems is full of rich physics and can have potentially disruptive technological applications as well. And I acknowledge my collaborator, Professor Ranjan Barman. He's in India and he does the TR-MOKE studies. So we do all the fabrication, design, and interpretation, and he does the TR-MOKE studies for us. So that's it. And I'm done. I thank you very much.
Thank you. Then now we go to questions.
Yeah.
I have a question about that mode of 4.5 gigahertz. How thick are the nanomagnets?
Oh, they're typically between 2 and 15. This one, I think, was 6 nanometers.
Nanometers. So is there a possibility that you're sensing the piezoelectric response from the substrate? Because the penetration depth of your laser beam is probably larger than 6 nanometers, even if it's a metal.
Oh, absolutely. So that is a possibility but if that was the possibility, then the frequency would be the frequency of the laser repetition rate every year. Unless we're limited by the piezoelectric response of the time of the surface.
Right, so
It's all 60 picoseconds.
So you might be driving the same way that you're saying that you're hitting.
That's a possibility. We actually, the other possibility is that the laser field has an electric field, right? It's an electromagnetic wave. So there's an electric field component, and that electric field can also cause a piezoelectric response. So there's a strain that is related to that electric field.
At megahertz, you're probably below kilovolts per.
No, this is not megahertz, this is gigahertz, 4.5.
No, the laser, I guess it's an oscillator, you're doing 80 megahertz. Why the fluence that you're using, I don't think you were having such electric field. But I guess that
So that is the conjecture. That's why I think that there will be some contribution from it, but certainly not major contribution. The major contribution we think is due to laser heating and cooling. And that has been observed by others as well.
But so I guess my question is laser heating cooling often nanomagnet or all the piezo?
No, not neither. It's the laser heating and cooling is actually causing both the nanomagnets and the substrates to expand and contract.
But that assumes then that you are coherently transferring heat to a phonon.
No, it's not coherent. It's just heating and cooling. It can be incoherent. If I shine a laser on this table, I'll heat this table. Right. And then let's say that this table is resting on the carpet.
Right.
And I'm heating the carpet as well.
Right.
But their thermal expansion coefficients are different.
Right.
So they're expanding at different rates, and that is causing a strain.
Right.
And so that strain is what you're observing.
But why do you see a single mode associated to that strain? Because
we don't always see a single mode. Sometimes we see 2 modes. So, but there's one dominant, and that dominant mode has to do with the difference between the rate of expansion and contraction of the nanomagnets and piezoelectric substrate. But we can see higher order mode, we see higher harmonics also. And in one case, I told you that in one case, what happens is that these modes can attenuate quickly also. But let me go back and geez, I'm out of it. I don't know why about that. There was one case where I showed that the wavelength of that mode corresponds to the pitch of the array. So that is also something that others have seen. So these modes, as they travel through the piezoelectric substrate, they get reflected from these magnets, so distributed reflection. And so when their conditions are right, that is when they have a 2 pi modular 2 pi phase difference, 2 pi phase difference or 2 and pi phase difference, they will actually build up coherently, and so you see a stronger effect when the wavelength matches. And there is a theory paper from University of Illinois at Chicago that has simulated this, and it's cited in my paper, but I don't have it here. If you look at my paper, it's cited. It's from University of Illinois at Chicago. They actually simulated this effect in an area of all things, in an area of nanomagnets, and they showed that you'll have multiple modes corresponding to, say, you have four of them, 4 magnets, right? So you have one periodicity along this direction, one periodicity along the diagonal, etc. So they claim that you will see different frequencies corresponding to the different periodicities. And we actually see that also. We see the diagonal one and we see the lateral one. The one that we do not see is the particle. For some reason, I don't see that one. I just don't see it. Yes.
So there was this one slide where you were showing some deviation from Kerr points. I think it was like so if I understand it correctly, then in Kerr mode we have this gyromagnetic ratio, right?
Yes.
Which gives you the slope. And there was one part like where it was flat, and then after a certain magnetic field it goes like this. But you were mentioning that the slope does not match with the Kerr mode.
So there are some modes whose magnetic field dependence obeys exactly the Kittel formula. We call them Kittel.
Right.
If they do not obey the Kittel formula, then they're obviously not Kittel modes. Right. So there's
like I think you mentioned something that it's because of SCW that there's some coupling that slope.
so if it does not follow the Kittel mode, not just the slope, but through the entire magnetic field wave, if it doesn't follow the Kittel mode, that means it's not a pure spin wave. That means something else is mixed into it. In this case, that something else is usually phonons from the soul, whether that is generated by periodic laser heating and cooling or externally launched surface acoustic wave. So once, if you have a mixed mode, that's not a pure spin mode, then you will not follow the Kittel relation. So anytime you don't follow the Kittel relation, you know it's not a pure spin mode. It's a hybrid mode. So spin has been hybridized with something else. What is that something else? In the case of it can be plasmons, it can be phonons. So it depends on what we have. So if it follows Kittel mode, it's not interesting.
I'm wondering if there are like any examples where the gyromagnetic ratio deviates slightly from the Kerr mode.
Then yeah, but that will still pretty much follow the Kittel mode. If it that we actually there are two things that go into the Kittel formula: the gyromagnetic ratio and the saturation magnetization. Right. So both can deviate slightly. And in fact, if you can fit it with the saturation magnetization that's slightly different from the textbook value, we do it and we call it Kittel mode. In this case, most of the times that happens because the saturation magnetization in a nanodot is not the same as the saturation magnetization in pop. Because in a nanodot, the saturation magnetization is usually smaller. And it is smaller because the magnetization along the boundary is off. Right? So saturation magnetization will decrease if you make a nanomagnet out of it.
I have some questions. I will save that later, but I guess we had sufficient discussions. That's thanks super much.
Thank you. My pleasure. Return this to you.
Good. I will take care of this. So you will go with Xu Feng to see his lab.
Okay.
Xu Feng, yeah. Okay. So Sabrina will with you.
Yeah, I think we're meeting next. Okay. All right.
Thank you.
Sure, thanks.
You were take care of.
Yeah, I'll take care of these. What Adrian said.
So since we're really, yeah, only client, so we